Thank you very much. So happy to be here and to
Sorry. So Stanley DURRLEMAN, if you don't know him, so he's from the Institut du Cerveau, Brain Institute. Thank you.
Thank you, Pierre-François. And so happy to be here with you this afternoon to share you some of the research updates I have been doing. So first, so I'm an engineer and mathematician by background, so please apologize all my ignorance in many medicals and biological stuff. My research has been focused on the modeling and predicting the progression of neurodegenerative diseases, not specifically for one specific disease, but more generally for all type of age-related diseases. I will give you some examples on ALS. I've been working more recently, but you will see also more examples in Alzheimer's disease, and we have also applied that to other diseases like Parkinson's and Huntington's. So to give you a bit of the context of the question, we were interested at the beginning is to show you this kind of growth curve that you all know. So it's the weight, so you know how this works. If you have a kid, then you can report the weight of the kid at the age. So at 9 months old, a kid weighs 9 kilos. So you report here the dot. And the way you read these curves is to say, well, this kid here is within the normal range for a given reference population. That's the way you use it. And that's the same of concept we would like to extend, but not for growth, but for aging or age-related diseases. And this raises different difficulties. So I think one of the main difficulties is that age cannot be used as a marker of disease progression in aging in general or in the progression of a neurodegenerative disease. Okay, you can be 80 years old and be at very different disease stage at the same age. So it does not make much sense to align the data of different individuals with age. Another limitation of this growth curve is that you want to read them from the left to the right and see, well, this is how a kid grows over time, but if you have kids, you know it's not going to happen this way. And the dot here does not tell you anything what will happen in the next month. So your kids in 18 months can be all above the curve or below or in the middle. So these models are descriptive. They are done using cross-sectional data and could not therefore predict the progression in the future. And the third limitation we want to tackle is also the fact that these growth curves are what we call univariate in a statistical sense. So here you look only at the weight. Of course, you know there is the same curve for the age, but you have the two parameters modeled separately. So you don't have the joint distribution, as we see in statistics, between the age and the weight. So you might be normally thin and normally high, but the combination of the two might be atypical for a reference given population. That's why we have the body mass index to do that. So it works with two parameters, but if you have many more parameters, then what you need to do is to model the joint distribution of the parameters and not only the distribution of one parameter at a time. So here I present briefly the construction we have ended up to address these different issues. So here on the left-hand side, what you see, so on the x-axis is age this time, and on the y-axis is a normalized biomarker. So let's say it's height and weight. If you, sorry, it's going too fast. Height and weight, so you have two biomarkers, one blue and one red. And suppose at the moment that we have these two curves that depicts how these two biomarkers evolve during disease progression, on average in a reference population. And then what we see here is one patient that has been seen at 4 different time points, so at 66 years old, 67, 70, 72. And at each visit, we have measured the two biomarkers, the blue and the red. And now we want to explain, to describe what is the difference between the progression that we see in this particular patient compared to the scenarios that describe the progression at the population level. So that's fairly easy to explain. So what you see typically is that this patient has an earlier onset compared to what is predicted by the population model. So you have parameters that basically shift the curves to the left, saying that, okay, here the age at onset is different between the model and the patient. If you correct for that, you still see that there is still differences. And one other difference is that the patient progresses slower than the model. So you have another parameter that can change the dynamics of the time axis to account for the fact that the patient here has different pace of progression than what the model predicts. And even if we correct for these two things, so what you notice is that still the dynamics of onset between the blue and the red biomarker is different. Okay, at the same disease stage, so the difference between the blue and the red is way greater in the model than in that is seen in the patient. So we have another set of parameters that can, if you wish, change the relative dynamics among the different biomarkers once we have aligned disease stage and pace of disease progression. So that's a way, by a certain number of parameters, we can describe what is the different dynamics between a model and a patient. Now, of course, the question is, how do you build the model of progression at the first place? So for doing so, we use longitudinal dataset where we see multiple patients at multiple time points. So let's say we have patients A that we have seen 4 times, B twice, C 3 times. And then we estimate these two logistic curves here such that it represents the most typical patient in this population, in the sense that the average of all the parameters here that map the model to each patient has an average of 0. So, which means that the age at onset by the model is the average of age at onset in the population. And the slope of the logistic curves is such that is the average speed of progression observed across the different participants. And the distance between the two curves represents the typical time shift between the onset of the blue and the red biomarker. So that's a way we can build a model that is representative of the progression of the population, plus all the parameters that position each participant with respect to this model. So this is just another video example of the different parameters. So time shifts, which accounts for the difference in age at onset, the pace of progression, where we see the curve going slower or faster depending on the patient. And here we see how we can change the relative timing among the biomarkers. And you see that here you have something which remains stable in time, which is the stage of progression, which is constant, and the only thing that changes is the relative value of the biomarkers at the same stage. So just to go maybe one step further here what I represent is exactly the same thing at the bottom. It's just another representation of what you see on the top. So here on the bottom, here on the top I have age, I plot the biomarker against the age. Here in the bottom, instead, I plot the first biomarker against the second biomarker. Okay, so when I have 2 dots here, now it's just 1 dot, and age time becomes implicit in this representation, it's not seen. So you see the progression of the participants here, so it's 66, 68, 70, 72 years old, the patient progress here along this trajectory. Oops, what happened? And the 2 curves on the model is actually one single curve, which connects this corner here, 0, 0, when this is the most normal state of a person, up to the corner 1, 1, which is when the 2 biomarker becomes the most abnormal. And the shape of this curve here depends on the relative timing of the blue and the red biomarker. And that's the trajectory of the population. And so you see that the 2 parameters here that just change the dynamics of change of the progression does not change the trajectory itself. Just change how the dots, if you wish, are plotted in these curves. So the plots corresponding to 66 years old, it was at the beginning very far in the corner. Now it's plotted in face of this, in front of this dot here. And here you change the time interval between the different dots. And at the end, only the second one change the position of the trajectory in the space, meaning that here the presentation of the disease is different from the model to the patient. And I like this representation because it looks a bit more like what we have seen in the growth curve at the beginning. And it allows us, I think, to see a bit more clearly how this model can be used. So here at the center is the same representation, so biomarker 2 against the biomarker 1. The average trajectory is the central curve here. And I plotted all the different curves here that depicts the variation in the population. Okay, that's somehow the variability range of the trajectory in the reference population. And now I have three patients, 1, 2, 3, 4, and I just plot the I plot the patient data in this representation. So patient 1, if you plot the data, it just falls here. So you can straightforwardly, I think, see that the patient 1 is an early onset patient, yeah, at the early disease stage. And we have a beginning of disease trajectory, which is, I mean, quite typical to what is observed in the reference population. 2 here is at a slightly more advanced disease stage, but still very well typical. More interestingly, patient 3, the data falls here, so you can see that patient 3 is completely atypical compared to the reference population. That is quite obvious because, of course, if you see only one biomarker at a time already, the biomarker has quite atypical value. So it's not very difficult to see that 3 is not in line with normal range in the population. 4 is slightly more interesting because 4, all the data of 4 fall within the normal variability range. What is atypical in the patient 4 is the direction of change. The dynamic of the patient 4 is not in line with what has been described in the population. What does that mean? It just means that it's very unlikely to see the red biomarker being so steady, while at the same time the blue biomarker show such a sharp increase. So here again, you see that the model allows to finally identify the patient. So where is the disease stage? Is the value of the biomarker typical or not atypical? And what is the typical trajectory of change for the participant? All right, so now that was for the theoretical background. So I'll just describe some of an example. And the most recent one is on ALS. And for that, we use the PROACT dataset. So you're probably familiar with it. So a longitudinal dataset. And we split the dataset with 4 different subtypes according to gender and to the site of onset. So either spinal or bulbar subtype. And so you see you have a fairly high number of visits per patient and quite a decent follow-up time. And so we use that to build this model of progression, and we plot here. We used 4 different subscores of the ALS-FRS. So respiratory, bulbar, fine motor, and gross motor subscore of the scale. And what you see here is the 4 different models for women and men and patients with spinal or bulbar onset. And that has been replotted into the normal range of the scales. So of course you can see quite large differences across the different subgroups, which is of course fully expected. And of course, we have, since all that is parameterized by parameters, we can do a statistical test to see what are the significant differences across the different subtypes. I won't go into the details. I mean, it's more validation experiments and something you will not learn something really new, but I think it's nice here to retrieve, for instance, that the body mass index decreases earlier in women than in men. And that is independent of the site of onset, or also that the fine motor scale changes earlier in women than in men, and whatever site of onset, for instance. And here, again, to appreciate this result, you need to understand that when we say earlier or later, we have discounted the fact that patients might have different pace of progression and different disease presentation. And that I think is quite unique, because usually in studies, for instance, you have a lot of confounding factors in the way we analyzed either the age at onset of the pace of progression. Coming to a disease I'm a bit more familiar with is to Alzheimer's disease, and to try to switch from something descriptive to something which is more predictive, because I said in the introduction that what we're interested in is not only to describe a progression, but also to predict the progression. So that was something we have done in Alzheimer's disease. So here I used 5 different cohorts from the USA, Europe, Australia, and Japan. So with also in total, I think 4,600 patients, and a different number of visits and follow-up duration. I use a certain number of biomarkers here, so it's either imaging biomarkers, CSF biomarkers, and some cognitive scales at the end, so DASCOG, MMSE, CDR sum of boxes, which are 3 cognitive batteries. So at the end, what we do is, so that's the model that we estimated at the end using so a subset of this of the collection I have presented before. And so you see this spaghetti plot showing the different progression of the different biomarkers. Okay, what we can do with that, we can fine-tune and do similar analysis, descriptive analysis to what I have presented for ALS. So of course we can dig into the impact of different genetic markers and so on and so forth. But here I would like to emphasize on something a bit different. The interest of the model is, the promise is to be able to predict the future of the progression. So how we can do that? So here I just use only 3 biomarkers for the sake of simplicity. So imagine I have built this model in this population, and now you have a new participant coming in, a new patient that comes into the clinic, for instance. What you can do is, of course, to measure the different biomarkers. So here an amyloid PET, an imaging biomarkers, another MRI biomarkers, and a clinical scale. Okay, you have a patient at 70. You measure 2 of them, for instance. So you convert that into a 0-1 scale, and you report the dots here. Maybe you have seen these participants 1 year apart, and at 71 you report 2 of these data. And given these 2 visits of the participants at 70, 71, we can estimate the best parameters that explain the progression that is seen here. So the most likely progression the participant is to display in the future. And at the end, it's very easy. If you want to predict what the participant will be at 75, you just read here the 3 dots, and you convert back into the native scale, and you say, okay, the participant who has an amyloid PET at 70 centiloids at 70 years old, you predict it will be at 90 centiloids, and you predict that this cognitive scale would be at 7.2 from 0.5. And that's exactly the way we can use it so to assess the prediction of a given patient. Of course, the big question here is how to evaluate this prediction against the true observations. So to do that, we have done a very extensive validation study. So we used for estimating the model only the amyloid positive participant in the US database, okay, and to build the disease progression models. And then we used all the other participants of ADNI and all the participants of the other study as external validation set. For one of these participant in the validation set, imagine we have a woman here with 4 different time points. We can change the different layout of the prediction. We can use the first visit to predict the second one. We can use the second one to predict the third one, the first one to predict the fourth one. We can use the 2 first to predict the third, etc., etc., you understood. And we can then assess a very huge amount of prediction for one given participant. And of course, since this is repeated for the same participants, you have a way to disconnect this prediction task into independent analysis. Long story short, yeah, so from the nearly 5,000 participants, we could evaluate the forecast, nearly 50,000 forecast for the ADAS-Cog, which is one of the scale, to nearly 100,000. And from that, we can, okay, so we have tons of different forecasts with tons of different settings. And we want to have the kind of the intrinsic measurement of the accuracy of the prediction system. So for that, we need to have a reference situation. So here the reference situation is a 75-year-old American woman that comes from this US dataset, who has an average level of education, no genetic risk factors, and clinical and positive biomarkers, and a mild cognitive impairment, from whom we forecast cognitive assessment in 3 years' time based on 2 past visits, separated by 8 months without missing data. So just to understand that when someone reports prediction performance, you can see in some articles, it does not make any sense without specifying exactly the setting in which you have made the forecast. So you see the number of parameters that need to be fixed. Given that reference participants, what we see is that our model here is so let's say for the MMSC, for instance, we make for this typical situation an error of 2.5 points of MMSC. So in 3 years' time. We benchmark that against deep learning methods, so recurrent neural network here, which give also interesting performance, and compare that with a linear mixed effect model that is usually used, for instance, in clinical trials to assess outcomes. Or the prediction, which is the most naive one, but sometimes very good, which assume the patient does not change over time, and the same as the last seen visit. So that's how we predict, and we have shown that in Open Data Challenge, we actually are better than 56 different alternatives that has been developed by other labs. But more interestingly, to see how this prediction performance changes when you don't predict for this typical woman, American woman, but for different types of participants. So I won't go into all the results, but we assess how the change in the setting change the performance. So if the block spot is on the left, it means that we have better performance than for the reference population. If it's on the right, it's a decrease in performance. So in the reference situation, we predict with 2 past visits. So if we have only 1 compared to 2, of course, the performance decreases a little bit, but you see it's decreased by less than 0.5. And of course, if we don't 2 but 3, we increase the performance also marginally. Interestingly here is that the model has been trained on American participant, and when it is tested on Japanese participant or European participant, actually the performance is even better, which shows that the model can generalize to unseen ethnicities. So that's a way we can assess the prediction of the model. But then the question becomes, okay, it's good. You can forecast to some extent how the participants will be in 3 years' time. But how is that useful in practice? So there are different answers to that. So one I would like to focus here is the way we can select participants at entry of a trial. So the idea is quite simple. Neurodegenerative diseases progress usually very slowly. So I know it's not so true for ALS, that has a shorter overall duration. But if you think in Alzheimer's or Huntington or Parkinson's disease, it progresses very slowly. If you have a drug or an intervention that you think can slow the progression of the disease, to show that, you need to include participants with a fast disease progression. Because if the participant is steady, then there is no way you can show that your intervention will decrease the slope of change, because the change by itself is very small. Okay? So the faster the progression for the participants, the higher the effect size, and the more powered the trial. So that's what is explained here. When we do a clinical trial today, we have some inclusion criteria, which is basically some very rough, I would say. And we select a population that is very heterogeneous in terms of progression profiles. So in this population, you have participants that will progress nearly very little during the trials. Other ones will develop the disease very fast and with a lot of different presentation. And that's what makes the clinical trial in this setting very difficult, and why the sample size are very high. And so what we claim here is that we need to select the fast progressor. So imagine we have this clinical scale as the outcome, the primary outcome of the trial. All the game is at inclusion to include participants for whom you can have who will experience the fastest prognosis, the fastest change for this outcome. Of course, we don't know at the end of trial how the patient will progress. But given that we have a predictive model, we can here make a prediction of this amount of change that will be seen in these participants at the end of the trial. And then you can split the population into two, the one you predict to be fast progressor for this outcome, and the one you predict to be slow progressor for this outcome. And then, I mean, by design, if your prediction is good enough, then you can increase the effect size and reduce the sample size. And to demonstrate that, we have simulated different kind of trials. So here again, so it's in Alzheimer's disease. We use the setting of 6 different clinical trials that has been done in for real. And we say, what if, instead of including the participants as they did in this trial, we stratify the population into fast progressor and slow progressor, and how this could change the outcome of the trial at the end. So the first question is to ask is, in this, for a given trial, how well can we predict that the participant will have a fast or an important progression of the outcome of the trial? So that's the ROC curve analysis. So what we see here. So if the system would be completely random, then the curve will be along this diagonal. Of course, the best predictor ever would reach this point over there, but it's a very difficult task to do in this setting. And here, so you see the ROC curve with an AUC at 76, 73%, depending on if we use our model or a deep learning model. And so that's the way you see that the prediction model, I mean, it's not super perfect. Okay, we do some errors in identifying the fast progressor. So in the machine learning community, having an AUC of 76 is not good at all. But for this specific task, which is extremely difficult to do, I mean, it's decent. Okay, is that good enough for designing clinical trials? So the answer is yes. So here it used to be a confidence interval, but they don't display here. I'm sorry about that. So that's a sample size analysis for the trial. So here is the percentage, the hypothetical treatment effect. So 22% here means I have a drug that I hypothesized will decrease the rate of change by 22%. If you do that without any other selection method than what is currently done, you need nearly 900 participants per arm. Yeah, that's what you need usually. If you select participants with, for instance, genetic risk factors, which are more likely to have a fast progression, then you can already decrease this number of participants by 70 or so. But if you use a prognosis score using a model that can predict the progression of the disease, then you can further reduce the sample size to 500. So depending on the setting, depending on the outcome chosen, depending on the trial duration, depending on the population targeted, overall, we can always significantly reduce the sample size from 38 to 50%, depending on the setting. So even with a model that does not predict extremely well, still the performance is good enough to significantly reduce the number of participants in trial and to do way more powered trial than what is done currently. So as a conclusion, so what I presented is nothing but a way to build disease progression models where we can finally parameterize our participants, the different biomarkers of participants changes over time by adjusting age of onset, pace of progression, and disease presentation. And that allows us to forecast clinical endpoints in imaging biomarkers up to 5 years in the future, and to select then the participant in a trial to do a more powered clinical trial, meaning decreasing the sample size. One thing I have not presented and that I'm really interested in is to use also the model as a digital twin of the participants, okay? Or sometimes it's called synthetic placebo arms. So meaning that the prediction of what the model will become can be its own placebo, to which you compare the effect of the drug. And so you have the hope to describe the effect of the intervention at the individual level by measuring the difference between what the model predicts to what is observed with the intervention. So I have the first papers have been published for Alzheimer's disease, but we also have published one paper in Huntington, one in Parkinson's disease, and so recently in Journal of Neurology, one for the ALS. Thank you very much for your attention, and we'll be happy to answer any questions.